We begin with a simple scenario. Our digital-to-analog converter has an input-output characteristic denoted by function f. We assume a static nonlinearity, modeled as a polynomial, creating a nonlinear relationship between x and y. To counteract this, we consider predistortion. However, predistortion does not support real-time or background correction. Our goal is to ensure the baseband signal W and RF output Y contain the same information. This requires minimizing the difference between f of x and w, making it as close to 0 as possible. We define an error function, g of x, as the difference between f of x and w. The system must compute x so that g of x equals 0, effectively solving for the root of g of x. A well-known numerical method for this is Newton-Raphson, which iteratively refines an estimate. It updates x using the formula x of n plus 1 equals x of n minus g of x divided by its derivative. By continuously computing this, the circuit dynamically adjusts x in real time, ensuring signal fidelity. This simple yet effective method enables real-time correction without predistortion limitations. Alright, here's how it works. We start with this equation and make a simple approximation. We assume that the derivative is 1. While this is not exact, it simplifies calculations. With this assumption, the next value of x is the previous value minus g of x. Since g of x is the difference between the output and input, this simplifies to the present value of x plus the baseband input minus f of x. Now, let's build this in a circuit. The baseband input and f of x are at the output. To implement the equation, we subtract f of x from the baseband input and add it to the previous value of x. To introduce the required time delay, we use a z-1 block. This circuit follows a simplified Newton-Raphson technique, ensuring that f of x closely matches the input. Interestingly, the circuit in the dashed box resembles a digital integrator. With a feedback loop and an integrator in the forward path, this forms a delta sigma modulator. By placing the transmitter in this loop, we achieve high gain at low frequencies. The high loop gain ensures that the output closely follows the input, despite circuit nonlinearities. This provides several advantages. First, it corrects nonlinearity in real time and adapts to temperature variations. It eliminates the need for lookup tables or FER filters and does not require adaptation. The key contribution is recognizing that delta sigma modulation is a simplified Newton-Raphson technique. Additionally, by placing the transmitter in this loop, we improve its linearity. To refine the approximation further, we explored better methods for G', improving performance. One challenge is that the system includes both analog and digital signals, requiring an ADC. This ADC must achieve high resolution while operating at high speeds with minimal power consumption.